All right, so chapter 20 is all about electrochemistry, and we're going to see that this focuses strongly on reactions where electrons are being exchanged, right? Electrochemistry, electrons. Eventually, we're going to build up to where we can sort of look at this diagram of a voltaic cell, also called a battery, and understand exactly what's going on here, right? So batteries are becoming an increasingly important source of energy, especially as fossil fuels and sort of more combustion style reactions are coming out of favor because they produce carbon dioxide. So these are becoming increasingly more important in our world. And so that's what we're going to sort of be building up to, is understanding how exactly batteries work. All right. So before we can do that, we need to, sorry, hold up. Kind of review some stuff that we would have talked about before regarding important reactions here. There's a specific type of reaction that's going to be very important called an oxidation reduction reaction. And so this would have been something that would have been discussed previously in the previous semester. It's coming back here. All right, so let's just take a look at an example real quick. We have something like aluminum all by itself reacting with a copper ion and converting into an aluminum ion and solid copper. Okay, so this is a fairly straightforward example here. We can see how we're going from something that's neutral, like aluminum all by itself, solid aluminum metal, to the aluminum ion. So the only way that that's going to happen is if this aluminum loses electrons in the process, right? Loses, in this case, it would be 3 electrons. And we can see our copper is going from being this charged copper ion to then having this neutral charge. So the only way that that's going to happen is if the copper then gains, in this case, 2 electrons. So what we can see what's happening in this reaction is this exchange of electrons, right? The aluminum is losing the electrons, it's giving it to copper, the copper is gaining the electrons, right? So this is a feature of these oxidation reduction reactions. Really, these are reactions where you have an exchange of electrons. So we can just make a note, we have exchange of electrons. All right. So first thing we need to be able to do is to determine what element is being oxidized and what element is being reduced in an oxidation reduction reaction, right? So I'm going to make a little table here. On the one side, we're just going to list the elements. Okay, and we want to figure out what's called the oxidation number is on the reactant side and the product side. And again, what we're finding is oxidation number or oxidation state, same thing. Okay, so there's this set of rules that we're going to sort of have to apply here. Okay, and so let's just go through these one by one here, looking at our chemical equation. The very first rule says that the oxidation number of an atom in its elemental form, meaning it's all by itself and not paired with anything, is going to be 0, right? So if you have a neutral atom all by itself, its oxidation number is 0. So based on just that rule alone, I can assign 2 things on my table here. I can assign the aluminum on the reactant side. That's got an oxidation number of 0 because it's aluminum all by itself with no charge. And I can also assign the copper on my product side because it's copper neutral all by itself. So that would also have an oxidation number of 0. All right, so again, that first rule is if it's in its elemental form, meaning it's all by itself and neutral, it will be 0. All right, the next rule says that for a monatomic ion, the oxidation number is going to be the same as the charge. So for this, in this case here, let's just pick apart that word real quick. Monatomic, what does that mon mean? 1, right? So a single atom ion, its oxidation number is just going to be the same as its charge. So if we look up here, we can actually finish this off. On my reactant side, my copper's a monatomic ion, so it's going to have an oxidation number of +2. And on the product side, my aluminum is a monatomic ion, so it's going to have an oxidation number of +3. Okay, now importantly, we have some terminology here. Like we said, these are oxidation reduction reactions. The thing that is losing electrons, so in this case, it's my aluminum that's losing these negatively charged electrons. We call that oxidation. And the thing gaining electrons, we call that reduction. People remember this using the acronym LEO. Losing electrons is oxidation.
Okay, then. So,
be honest.
I'll probably just go with my.
Okay. To be honest, I think it's easier to look at what's being reduced, because what's being reduced is going to go down in its oxidation number, right? That kind of makes sense. Reduced, it's going down. You can definitely remember it this way. Losing electrons is oxidation, LEO. You just have to keep in mind that electrons are negatively charged. So if something's losing electrons, it's actually going to go up in its oxidation number. All right. So we've only used, there's some other rules on this table, but we've only had to use these first two here. And you can see that oxidation number is really something that's kind of analogous to charge, right? So if something's neutral, it's got an oxidation number of 0. If something's got a net charge associated with it, its oxidation number is that charge, right? So it's giving you an idea of where electrons live in a particular atom or ion. And again, these oxidation reduction reactions are going to be all about exchanging of electrons, right? So something's going to be losing electrons, something's going to be gaining electrons. All right, let's do a slightly more difficult example here. Okay, another common, oh, whoops, I guess I don't have to get rid of that. Another common sort of application is going to be not just having monatomic ions, but having some polyatomic ions in there. And that's going to make finding the oxidation number a little bit more tricky, but it's not too bad. So let's take a look at an example. We have iron with a +2 charge and the polyatomic permanganate ion going to iron +3 charge. And finally, the manganese ion with the +2 charge. All right, so we're going to apply this set of rules here for calculating oxidation number. Make one more little room for myself. You got to add one more level for the oxygen. Okay, so we're going to do iron on the reactant side and product side, the manganese on the reactant side and product side, and finally the oxygen. All right, so I want you guys to take a minute and see if you can't fill in as much of this table as possible based on those first two rules that we talked about. The one thing that you're going to get stumped on at this point is going to be how to deal with this polyatomic ion. And so we'll deal with that in a, I'll show you how we deal with that here in a moment. But for right now, see if you can't figure out these boxes here. right? What was the iron on the products and the reactant side, and what is the manganese on the product side? All right, and then we'll do our first iClicker for this box right here. You're going to tell me what iron's oxidation number is on the product side for our first iClicker question of the day. All right. So indeed, because this is just monatomic ions on either side, its oxidation number is going to be +2 on the reactant side and +3 on the product side. So then I want you guys to take a second and tell me whether this, before we can even have to go forward, we can already sort of say whether A, this iron is being oxidized, or B, the iron is being reduced. All right, so take a second, and again with the iClicker here, tell me whether or not our iron is being oxidized or reduced. All right, so remember, reduced means it's going down in oxidation number. In this case, since it's not going down, but going up, the iron is being oxidized. It's losing electrons, but electrons are negatively charged, right? So if I lose a negatively charged electron, I actually go up. All right, so the other box that we can fill in here is the manganate on our manganese ion on our product side. It's just a monatomic ion, so it's the same as its charge. Okay, so then how do we deal with this polyatomic ion? We got some other rules for that. So if we just sort of read through them, we went through these first two. All the other rules then apply to specific elements. And again, what's going to make this a little bit different than just strictly being this idea of charge is now we're going to extend this concept to covalent compounds as well. So this permanganate ion here is manganese covalently bound to 4 oxygens. All together, they form this polyatomic ion with this -1 charge. But the manganese and the oxygen are actually covalently bound to one another. This concept of charge really only applies to ions, but this concept of oxidation number extends to both ionic and covalent compounds. So we're going to be able to assign the oxidation number of the manganese and the oxygen in that polyatomic ion. Okay, and it still relates, it's still a very similar concept to charge. It really tells you a lot about where the electrons in a particular compound live. All right, so the third rule is fluorine is always -1. That doesn't apply to us. The oxidation number of hydrogen is then going to be +1. Again, these are similar to what you would expect based on their charges of those ions. But again, this concept would extend even if you were talking about a covalent compound that had hydrogen or fluorine in it. All right, the next rule is that the oxidation state of oxygen is -2 unless it's combined with fluorine. And that's kind of an odd caveat. I mean, it's an important caveat, but there's literally only one compound where that would be the case, and that would be oxygen difluoride. So unless we're talking about that, we can say that the oxidation state of oxygen is -2. Okay. And this is an important rule. So if I had to like prioritize these rules here, if I'm not, I mean, obviously we want to know everything, but if I'm going to only be able to fit certain amount of information in my head, this first rule is very important. The second rule of monatomic ions is very important. And then the one with regard to oxygen is important. And that's just because so many of our polyatomic ions, phosphate, sulfate, carbonate, all these polyatomic ions have oxygen in them. And the polyatomic ions tend to be the tricky ones. So just remembering that oxygen is -2 is really important. Okay, so that means that we can fill in that -2 box for oxygen. Okay, it doesn't appear on this side, and we'll talk about why that is here in a second when we talk about balancing these chemical equations. Right now, we're going to focus on the manganese. Okay. So how am I going to figure out what manganese is? Well, since I know what oxygen is, I can then use the rule that says that the sum of oxidation states in a polyatomic ion must equal the charge of that ion. So I know for my manganese here, I don't know what my manganese's oxidation state is. So we'll just say, leave that as just manganese. But I do know that I have 4 oxygens, each with the oxidation number of -2, and everything has to sum up to that net charge on my polyatomic ion. So again, I don't know what my manganese is, but I know that this is 4 times -2 equals -1. Right? So then if I do my math, it's what -8 would give me -1. I can, rearrange this to figure out that the manganese has to be +7. Right? So again, another important rule here, because it's going to help us deal with our polyatomic ions, the sum of the oxidation state must equal the charge on the ion. And I mean, really, it's just the sum of the oxidation states have to equal the charge, regardless of whether it's neutral, then they should sum to 0, or if there's a charge, it should equal the charge on that polyatomic ion. Right, so those are out of all of these rules here, those are the 4 that I would sort of prioritize to keep straight in my brain, because they're the most important ones. And so, like we said that the iron was being oxidized. The manganese is then, we can see, being reduced, right? It's going down in oxidation number. All right, so hopefully these oxidation numbers are a bit of a review, something that you would have talked about previously, but importantly, this is the set of rules that we're going to apply to determine what's being oxidized and what's being reduced. All right, so that's the first skill that we need, is given a chemical equation, can we calculate oxidation numbers and determine what's being oxidized and what's being reduced? That's the first thing we need to know how to do from this chapter. All right, so now we're going to talk about balancing these chemical equations, and they're kind of a pain in the butt to balance, quite frankly. Okay, this is what's called the balancing by half reaction. All right, and again, our goal is going to be to balance this chemical equation here. Right off the bat, you can see that something's like abnormal compared to what we're used to here, because I have an oxygen on one side and that's not appearing over here at all. So I can't use my normal method for balancing, right? Truth be told, like when we kind of what the logic behind this is, when we summarize these oxidation reduction reactions, we only really care about the elements that are being oxidized and the elements that are being reduced. That's what's being shown in this sort of unbalanced chemical equation here. When we go to balance it, we're going to have to include some waters because those are also going to be involved in this reaction. So I'll show you what I mean here in a second. So first thing we're going to do, we're going to have this long procedure here. Okay. So step one, we're going to split into our oxidation and reduction reactions. So what do I mean by that? I'm going to take my oxidation reaction where iron, so this was my oxidation, the iron 2 ion. I'll be lazy with my signs here just for the sake of speed. Going to the iron 3 ion, and then my reduction half reaction is my manganese permanganate ion going to the manganese 2 ion here. All right, so I split into oxidation and reduction half reactions. And what we're going to do is we're going to like balance these half reactions first and then combine everything back together at the end. Okay. So the first thing that we do, so split into the oxidation reduction reactions, we're going to, it's called mass balance. Our half reactions. So you're going to look at each half reaction and just balance it in terms of the elements that are given there. Yeah, so that's exactly, we'll talk about our oxygens here in a minute. That's what we're going with. We're going to see that we're going to include some things that aren't originally in our equation, like water. But step one, we're going to mass balance our half reactions. Okay. And so we can see that in this case, meaning I'm going to balance everything other than the oxygens, right? So we can even state mass balance our half reactions. There was hydrogen there, I would also not pay attention to it. So I'm going to make sure I have the same number of irons on both sides and the same number of manganeses on both sides. In this case, they're already, that step two's already sort of been done here because of the way that this chemical equation worked out. All right, and now we're going to get to the other bit here. Make sure I got enough room. All right, so now we're going to balance our oxygens by adding water. All right, so I'm going to be introducing water into these chemical equations here, specifically for the sole purpose of balancing my oxygens. So in the case of this one over here, I don't have to worry about it because I don't have any oxygens. But in this one over here, my reduction reaction, I have this imbalance from the left and the right. So what I'm going to do is I'm going to add 4 waters over here. Right? And I'm adding 4 of them because I'm trying to balance these 4 oxygens over here. Okay, and it's like, okay, great. Now I've balanced my oxygens, but I've also just introduced a new problem here, which is the fact that now I got some hydrogens going on here that aren't on this side. So what the heck, why would I do that? So we're going to balance our oxygens by adding water. And then we're going to balance hydrogens by adding H+ ions. All right, so I can correct my imbalance here by then going over here and adding 8 hydrogen ions to balance my 4 water molecules. Each water molecule has 2 hydrogens. So now I've sort of corrected everything in terms of now I have all my elements present in my 2 half reactions here. Okay. But before I can sum these things back up, right? Now, the whole goal is to then I'm going to take these 2 half reactions and combine them back together at the end. I need to charge balance. All right. And so this is a little weird, but this is an important bit here. This is what these reactions are all about, is this exchange of electrons that's occurring. And so what I'm going to do is I'm going to explicitly include those electrons that are being exchanged in my balanced chemical equation here. So what do I mean by that? Well, let's just focus on this one right here. Right? I have this imbalance of my charges because on the one side, my net charge is +2. Whoops, that was ugly. And on the other side, my net charge is +3. So in order to charge balance this equation, I'm going to add an electron to this side, because now the total net charge on this right-hand side, if I combine my +3 ion and that electron, is +2. So this is been charge balanced here. I've explicitly included that electron in order to balance my charges. Okay, so we're going to charge balance by adding electrons. All right. So then let's look at this half reaction here. All right. The first thing that you're going to do is you're going to figure out what the net charge is on the left-hand side. So what's the charge if I sum all of this up? And what's the charge if I sum all of this up? Okay, so everybody take a minute and see if you can't figure out what the net charge is on either side of this reaction. I'm going to make a little bit more room for myself. Pull this down here. All right, and you can enter it in as an iClicker here. What is the net charge on the left-hand side? All right, so I have my permanganate ion with a -1 charge, and there's just one of those. And then I have 8 hydrogen ions, each with a charge of +1. So 8 times my +1 plus that -1 gives me a total charge of +7 on this side. Right? You have to account for the fact that I don't just have 1 hydrogen ion, but I have 8 of them. So each one's going to have a charge of +1 combined with this single ion that has a charge of -1. That's how I get +7 on that side. All right, and then on my other side here, I have a +2 charge for my manganese ion. I have 4 waters, but water is neutral, so that doesn't have any charge associated with it. So my charge over here is +2. So then how am I going to charge balance this chemical equation? my half reaction here rather. I need to make it so that the charge on both sides is equal. So what am I going to do? I need to then add, since I'm adding electrons, I'm going to add 5 electrons over here. Right? Because now my combined total from everything would be this +2 or +7 minus 5. That gives me that net charge of +2 on both sides, right? So again, the whole idea of the charge balance is you're going to add electrons so that you have the same charge on either side. Okay. So here's my half reactions here. And now I'm ready to combine these things back together. Okay. So we're going to combine. But we're going to make sure to do so in such a way that the electrons will cancel out. So what do I mean by that? So first of all, just notice that I have electrons on my product side for my oxidation reaction. And I have electrons on my reactant side for my reduction reaction, right? So if it appears on both sides of my chemical equation, I get to cross it out. Okay, but if I just combine them as is, I have 5 over here and only 1 over here. So those aren't going to cancel out. So what I'm going to do is I'm going to take this whole thing, my whole oxidation half reaction, and I'm going to multiply this whole equation by 5. Right, so that means, and let me just make some room. So that'll increase my number of iron 2 ions by 5. I got 5 iron, 3 ions, and 5 electrons. All right, cool. So now when I combine these two together, I'm just going to sum up my 2 reactions here. All right, so good with my state symbols now. Waters get that liquid designation. That's supposed to be an L. All right, so now this is what I get when I sum everything together, and then I'm going to go through and I'm just going to cross out what appears on both sides. In this case, it's just those electrons that cancel out. In other types of reactions, we'd notice that maybe there are waters or protons, H+ ions that we get to cancel out. So in any event, you'll just go through and cancel out things that appear on both sides, and that would give you your net reaction there. That's that. And all of this stuff. So here is my final balanced chemical equation here. All right, much more of a pain in the butt to balance than normal chemical reactions. This is just, again, by convention in terms of how these oxidation reduction reactions are presented. They're just showing the elements that are oxidized and reduced. They don't include the other things like the waters that are being involved in the reaction or the hydrogen ions that are being involved in the reaction. So you got to go through this process. And importantly, like one very important thing to notice here is if I had like just looked at this chemical equation, this first one here, even if I knew to add some waters or something like that, I still wouldn't have charge balanced it. There was no way for me to know that I was supposed to multiply this irons by 5 because there are 5 electrons being lost in that half reaction. Because my reduction reaction is gaining 5 electrons, right? So the fact that I had to multiply this thing by 5 is because of this charge balance step here, which is never something that we factored into our chemical equation previously, right? Or into our balancing previously. Everything that we had done previously for balancing chemical equations would have fallen under that mass balance sort of category. This idea of charge balancing is new, and it's specific to these oxidation reduction reactions where electrons are being exchanged. All right, so let's just practice this again. We'll sort of get our little cheat sheet rules here. All right, and let's do another example. Yeah, I guess so. All right, so step 1 here, right? Just, whoops, kind of combining all of our skills that we learned from this particular chapter thus far is we're going to first do our oxidation numbers for iodine, magnesium, and oxygen on the reactant side and the product side. All right, so I want everybody to take a minute and given this chemical equation, albeit unbalanced, I want you to go through and fill out this oxidation table here. All right, and I'll give you guys another minute or so, but when you get it, I want to know in our iClicker what the oxidation number of the manganese is on the product side here. No, it doesn't. The fact that this is a solid doesn't change how you approach it. Importantly, you're just going to pay careful attention to the charge, which is 0 because you have a neutral compound here. All right, so the iodine's easy because it's a monatomic ion on the reactant side, and on the product side, that's just iodine's elemental form. It's neutral all by itself. The permanganate ion, this thing here is actually the same one that we had previously. We found that the charge is +7, and we knew that because oxygen is -2 in that compound. And that's exactly how we're going to figure it out for this manganese oxide here. We know that oxygen's -2. And we know that whatever the manganese is, plus those 2 oxygens has to equal the net charge, which is just 0. So then my manganese, again, I don't know, but I do know that each of these oxygens are -2. So what -4 is going to give us 0? That's going to have to be +4. All right, and then again, one other thing that we should be able to do is, given these oxidation numbers, you should be able to tell me what's being oxidized and what's being reduced. So just take a minute and make sure that you can label what's being oxidized and what's being reduced. All right, we can see that it's our manganese being reduced because it's going down in its oxidation number. And that iodine is being oxidized because it's going up in its oxidation number, right? So it's losing that electron. All right, so again, first thing that we learned how to do for this chapter is just building these oxidation tables and determine what's being oxidized and reduced. That's hopefully review, but I know that it's something that's particularly tricky. All right, so moving on here, now we're going to balance this reaction using our half reaction method. I'm going to split it up into the oxidation half reaction and the reduction half reaction. Okay. That first step is to split everything up. So check, got that. The next step is to mass balance our half reactions. So anything other than the oxygens or hydrogens, we'll take care of those here in a second. Everything else you have to make sure is balanced. Previously, our previous example, everything was already balanced, so we didn't do anything at this step. I want everybody to take a look at these 2 half reactions and make sure that they're balanced without the oxygens yet. So we'll focus on the oxygens in our next step, but make sure your iodines and your manganeses are balanced. And what you should see is that you need a 2 out front of those iodide ions in order to balance it on both sides. All right, and now I'm going to balance my oxygens by adding water. So in this case, I don't have any oxygens over here to worry about. So let's focus on our reduction half reaction. I have 2 oxygens on the right, but 4 on the left. So I'm going to need to add 2 waters over here. All right. And then in order to balance, now I just introduced a new element that's not balanced, my hydrogens. So in order to balance that out, I'm going to add 4 H pluses over here on this side. So that gets us through our step 4 here. We balanced our oxygens by adding water and balanced our hydrogens by adding H plus. Okay. Now, one of the things that we hadn't really stated explicitly before is that this set of rules here apply to what's called acidic conditions. Because you're adding those H pluses, those acid protons there. So something, the problem would have said something like balance this oxidation reduction reaction under acidic conditions. Well, then what do we do if it says under basic conditions? We're going to do the exact same thing, the exact same procedure. But at this step here, we're going to insert one new thing at this step right here. We need to get rid of those protons. And so we're going to do that by adding OHs. Let me actually keep it that blue color so we know. We're going to add enough OHs to both sides to neutralize the H plus. Right? The bottom line is I do not want H plus to be in my equation at the end because it's not going to exist under basic conditions, right? So what I'm going to do is I'm going to add, specifically if it says to balance under basic conditions, you're going to add just enough OHs to either side to cancel out those protons. So in this case, I'm going to add 4 over here, and I'm going to add 4 over here. So whatever we add, we're going to add it to both sides. And so if we just want to kind of summarize here, we have 4H plus 4OH minus plus our manganate, permanganate. All right, and then importantly, what does this going to simplify to? If I take a proton and a hydroxide ion, what am I going to get? Hopefully we know that this will combine to make water. Okay, so I can simplify that by replacing those with water. All right, so this is an extra step that you have to add specifically if your problem says to balance under basic conditions. You're going to do the same thing up until this point, but now you got a bunch of H pluses in there that you can't have under basic conditions. So you're going to add enough OHs to both sides that neutralize all those protons, all those H plus ions. All right, so now I want everybody to take a minute and charge balance these half reactions. Right, what's my net charge over here compared to my net charge over here? And how am I going to add electrons to charge balance all that? All right, so this is -2, this is 0. So I'm going to need to add 2 electrons over here. All right, so take a minute and charge balance our reduction half reaction. All right, my net charge over here is just -1 because those waters are neutral. My net charge over here is -4 because I have those 4 hydroxides. So in order to charge balance this, I'm going to add 3 electrons to this side here. All right, that will now make this -4 as well. Okay, so now I get to combine everything together, but I'm going to specifically do so in such a way that my electrons cancel out. If I combine them as is, I got 2 over here and 3 over here. That won't completely cancel out. I need to get those to cancel out. The only way that I'm going to be able to do that, because they're 2 numbers that are not like able to combine with one another, is to multiply this whole thing by 3 and this whole thing by 2, right? 2 and 3 aren't going to cancel out, so I got to make them both 6. Their least common multiple. If we were fancy math speak about it. All right, and then I'm just going to make sure that that 3 distributes to everything inside my half reaction here. So when I combine, this would now be 6 iodide ions plus those 6 electrons. 2 times 4 is 8 waters, 2 permanganate ions. Oh, running out of room. All right. So then going through and canceling everything that's on both sides. This will cancel out my electrons, thank goodness, because that was my whole point. The other thing that will reduce here is notice that I have waters on both sides. I have 4 on the left and 8 on the right. So that means that this will cancel out and I'll be left with just 4 on this side. Right, so they don't cancel out completely because there weren't the same number on either side, but I will just subtract from my 8 those 4 that I removed over here. All right, a reaction that consumes 8 water molecules, but then generates 4 new ones is a net consumption of 4. So then summing everything up, I have my 6 iodide ions plus 4 waters plus 2 permanganates. Gives me my 3 iodine. And since this is basic conditions, I'm not left with hydrogen ions, but rather hydroxide ions. All right, so that was our first skill that we sort of had learned from this chapter, sort of summarized here. Given a chemical equation like this, we need to be able to do 2 things. We need to be able to determine oxidation numbers to figure out what's being oxidized and what's being reduced. And then lastly, we have this pain in the butt balancing method here called this balancing by half reactions that we need to do for this special type of reaction. And that's sort of what we laid out here in detail, was how to then go ahead and balance these chemical equations. So that's based on what we learned today. Those are the 2 things that we should be able to do. And so it's a good idea to practice those in your mastering chemistry homework.